6. 6. So it will give you, so you have, let's say we'll take 8. Yeah, we can bring it, beginning of week 9, Tuesday week 9, and you will have 1 more week for the MPPT, actually 1.5 week. You can deliver the last part end of week 10, So that would be the last phase of the project. We'll do the schedule of that. This is what I taught, last class about the observation and perturbation, and the other method was the incremental conductance. We talked about that one. These are the flowchart. I'm going to talk a little bit about the. More about the MPPT and how we are going to implement it. And after that, we are going to move on to the next phase. I'm not sure. Did Arnold give you the homework, simulation homework, or not? Yes. Did he give you? So that's the kind of start of that one, how the DC to DC converters, you need to design them. The one he gave you, you just do it by trial and error. But when we teach this part, you can see, hey, maybe you can go find out how much are those PI values for that controller. You guys can go calculate it yourself, It's going to take maybe a week or 2 to get there, but that's what we need to talk about. So, let's start from here. Wow. You can watch them?
Yeah, I mean, this was me like futzing around with it.
So you guys are going to select the perturbation and observation method, because this is simpler method. You select delta V, 2 volt, 3 volt, something like that for your project. I recommend you to use that one because it's easier for implementation, Use that one. But the incremental conductance is more effective and faster. But for the project, you guys are going to do both of them. They're going to give you a good answer. To be kind of everybody does the same thing, you'll use the perturbation and observation. Now, let's go back. See, I draw the block diagram for you guys, how you are going to control the ID, IQ, or P and Q independently from each other, right? We draw the block diagram, we talked about it, and you are going to do it in the next phase of the project. That's what you're going to do. Let's assume you guys did it, perfect, you're done. So what does it mean when I'm saying it's done? You have a 2 command. Either you can use the PQ command, right? P and Q command, right? Active or reactive. Or you can use the ID ref, IQ ref command, right? Because P and Q, they're going to translate simply, it's going to be like this. If you look at it, it's in the middle. If you look at it, we're going to have a P ref, Q ref, and you got the mathematical box, and you get the V value, right? And you get the IQ ref and ID ref. So basically, this part doesn't have any design. Just show some calculation. If you know how much is the P ref, how much is the Q ref, how much is the V, you can calculate ID, IQ, right? Now I want to connect this one to the MPPT algorithm. See what is going to happen. So let's look at a real system. What is going to happen? We have an inverter here, right? We have an inverter connected to a grid, right? battery, you are sensing the current here, right? These currents and the voltage, they're going to come to a control box. See, this is what I'm talking about. This is the inverter, right? Now we're going to look at it, See, let me talk a little bit about it. This inverter includes a power module here. You can write down the part number for this one and go look at it, in Infineon website, Right now, I think it's called, Infineon. Let me see which one. Oh, on this one, it says UPEC. UPEC was the old name of this company. Now it's Infineon. Write down the part number of this one and go, this is a three-phase, basically this is this. If you look at it, it's this. And each cross is a switch with an anti-parallel guide. And if you look at here, see, this is a DC connection. You connect your DC, whatever, battery, solar, whatever you want. You connect it here. This is a DC connection. These three, they are AC outputs, DC inputs. Now, there are lots of detail here. This is a kind of bleeding resistor. I'll pass it around. You can look at it, but I want to show you what's the real system. This is the gate driver. And when I designed this one, I didn't spend time on the gate driver design. Semitron had the gate driver package for this one. So just look at this blue one. 1, 2, 3, 4, 5, 6, 7, 8. I have 8. I don't know what's the other two. But when I give you, you can read it here. It said CLO, CLCU, BLBU, ALAU. This is A up. This is this switch. A up, A low. B up, B low. C up, C low. So basically, you bring 6 PWM channel, S1 to S6. We talked about it, right? You bring it to here. This is kind of expensive way, but very, very safe, You bring the signals from your control board to the inverter, right? This is all power. This board is all power, The control signals come here, goes to the gate driver, connect to the power module, right? And the power module is going to go, this side is going to go connect to the output filter and the grid, right? That's one side. This side goes to the DC source, whatever it is, battery or solar. Here there are some, you need some, voltage like 15 volt, 24 volt, for kind of, this gate driver, they are there. But this is the inverter board. You can pass it around, you guys can look at it. Now, this is a sensing board. Look at here. This is a sensing board. These are current sensor. These 4, you can see here. I will say, if you are interested, write down the part number and check it on the lamp. Go look at the data sheet. These are current sensors. 4 current sensors. 3 for here. 1 for here. I'm measuring a DC bus current also. I'm not sure the name is there or not. No, just I call it I input and output. Input output. I didn't give it a name. But there are. See, the current comes to here. Basically, if you look at this is kind of expensive way to build it. The current comes here, goes to the current sensor, and goes out. You know what I'm saying? Here, the same thing, and these are voltage sensors. These are again expensive. Each of these one they were about $40. This blue one there, each one is like $40. And this one about like a 15, based on how much current you want, but they're like a 15, 20 bucks. This one, So you measure the 3-phase voltage, you measure the 3-phase current, and just for extra measurement here, just I measure the DC bus voltage and current, right? So basically, this one doesn't do anything. This is just a measurement board, right? Now, here, if you look at it, there is some signal conditioning here. This is a active filter. Maybe you have it in the circuitry, those kind of things, op amps, those kind of things. All these things will be coming to this connector. Everything is reported here. So this one, here, there's a match connector there. This is a control board. This is a TI board. This is a control board. So this connector here will be connected to this one. Will be connected to this connector here, right? So basically all the current, voltage, temperature, whatever you want to read is coming here. I put some extra design here. Look at here. These are custom, just I want to make this board general to be able to use it for everything. I don't want to use it for a fixed project. So basically, you can unplug this one. This is another signal conditioning board. For example, I don't know. You have a new project, current and voltage value. They are different. For example, one project was 208, one project is 480. Maybe you are going to work with a 1 kV. So basically, you can only change this board. You know what I'm saying? Because DSP, the TI DSP, only accept 3.3 volt. If you go more than that, you're going to kill that DSP. So basically, you make sure whatever you are bringing here, you are scaling down to 3.3 volt. So this DSP, I think this one had, I couldn't recall it exactly, but I think it has 16 A to Ds. A to Ds is an analog to digital converter, they call it. So in the real life, you have an analog signal. You sample those things, you bring it here to get it. DSP is a digital processor, right? It doesn't deal with the analog signal. So you sense your analog signals, right? You bring it here to this board. From here, it's going to go to your DSP, right? DSP does all the calculation and everything. Now you can see there is this DSP is pretty powerful DSP. It has a 14 PWM channel. But for this project, the one I gave you already is passing around, I need only 6 PWM channel. Look at here, read when I give you this one, read here. See, there is a PWM 1, PWM 2, PWM up to there is a 1, 2, 3, 4, 5, 6. Yes. So there is a 12 PWM channels. These are for the inverter, 3-phase inverter. And there are 4 more PWM. This is for like an independent PWM channel. With this one, you can drive 2 of these inverters at the same time. This is designed for motor drive, they have a back-to-back inverter. So you can with one DSP, you can drive both. So what is happening, the DSP does all the calculation, I don't know, all the crazy things. This is the control box right here. This is here. It does all those calculations, and after that, it generates the PWM signals. PWM signals through these gray connectors. There is a auto connection. This one will be connected to that inverter. So basically, my control board is completely separated from my power board, right? It's very good this way, but it's expensive. This guys also, each one is like $14. This gray one, they're like $14. Those purple one, they are like $14. The project should be really important project to spend this much money on it. But at that time, I want to have a good board for general board, purpose board. I can do whatever I want. I designed this one. So this is a control board. This is the sensing board, and inverter board is here. Inverter board is connected to the source and load. They will sense all the signals here. It sends it to the DSP board. It sends it to the DSP board here, right? DSP generate the PWM signal, send it to the inverter. So basically, this guy, that's inverter. Let me make this one a little bigger. It got all the sensing. It could be temperature. We use this one for control. The one we are using only for control, I put here. But there are lots of fault signals. For example, they measure the temperature of the case of that IGBT. If it goes more than something, you have to shut down your circuit. You don't want to let it run because it's going to kill your inverter, right? There are tons of protection. We don't talk about those things. But it says the current and voltage is here. Now, this is a DC cap. On that inverter, I didn't put the DC caps, but if you look at the DC bus here, externally I can put my capacitors here. Right? These 2 points, they are available. These are the available points in that board. So I can connect my capacitors here, right? So this is where I'm connecting my capacitor. You can pass this to me. Now, in this case, I measured this current, right? And I measured, I don't know how to show you, this voltage. Right? This is what I have done. And it in the phase 3, you have a simple battery here, right? In phase 4, which I care, we have this. Basically, this one is going to measure I solar and V solar, right? This is the I sol and V sol, right? And what is going to happen? We do all these calculations, whatever, and we send the S1 to S6, right? This is the PWM signal going to the inverter. This is what we have in the phase 4. Now, let's think about how we are going to connect, because in the inverter box, this part we know how it does work, right? This part we know how it does work. We have a PREF, QREF, IDREF, IQREF, and the rest you know the story, right? So I want to show how I can connect these things to this. First of all, if you look at the PV curve, is like this, right? I short VS. Before getting to the MPPT algorithm, let's say we implemented the MPPT algorithm. I'm going to say inside this box, what there is inside this box. There is the MPPT algorithm, right? Which is going to get the I sol and V sol, and it's going to give me what? Vref, right? Vref is where I should go with this curve, right? So let's forget this one for now. I know how much is my Vref. 100, 200, whatever it is, right? I know how much is my Vref, so I'm not worried about this part right now. If I have my Vref, what does it mean? Yeah. Can somebody tell me? I want to have 200 volts, Vref. Basically, if you look at this capacitor, the voltage of this capacitor should be how much?
Vref.
Vref. It should become Vref at the end, right? So let's look at this capacitor. I'm talking about this middle one. I'm trying to relate how to connect this one to this. As I said, we know how this one works, right? So I have a capacitor here. This capacitor is this, right? I sol is coming. Let's say IDC is going out, right? If I want to keep this capacitor voltage fixed, what should be the relation between I sol and IDC?
Equal.
Equal. Why?
Because when we charge, it should go up.
Hmm? Let's say this is IC, right? And this is DC. And then this one is coming. This is I sol minus IC, right? And we know for capacitor, right? CdVc over dt, right? If I want my voltage be constant, how much is the dVc over dt?
0.
dVc over dt is 0, right? If Vc is a constant, so what does it mean? IC should be 0, right? IC should be 0. Now, let's think about it. If you remember, we said with the MPPT, this is the P curve, right? We said we start from here, we are going to go step by step by step. I don't know, I think this curve is kind of probably difficult. I'll put it here. We're going to go like this, right? We're going to go like this, right? So now look at here. So we are here at this point. I want to increase the voltage. right? See, my VREF, it says go to, for example, this one was 100 volt, it says go to 110, right? It says I want to, because I'm very far from here. For example, let's say this is a 200 volt, right? I'm going to go from 100 volt toward to 100 volt with a step of 10 volt, for example, right? So what is going to happen? This guy is telling me, hey, go 10 volts up. You're at 100 volts, go 10 volts up, right? So the VREF is 110. VC is 100. What should we do?
Lower IC. Increase IC.
Huh?
Decrease IC by decreasing IC.
Exactly. If I reduce my IDC, right? So let's say I'm here, I'm in balance point, right? I'm in 100 volt. If I'm balanced, staying here, what is going to happen? IC is going to be 0, right? The next command is saying, hey, I want 110 volt. 100 volt is not the answer, right? So the system should act such that this voltage goes up. To do that, what you should do, you should reduce IDC, right? So reducing IDC, now think about it. This bus is almost constant, right? Reducing IDC, what does it mean? Yeah, increasing resistance, but I want to hear another one. I want to connect down to this one here. What did I hear?
Increasing Q.
We decrease IDC. 100 volt. Let's say IDC was 10 amp, now it's 5 amp, for example. DDC was 100 volt. What is happening? What is happening? P is VI, right? Let's assume inverter is ideal, right? Let's say I 100% efficient, right? P is this side here, is this voltage, right? Times this voltage. This voltage times this current, right? VR, right? I said I reduce the IDC, decreasing power, right? Now, oh, I get connected to the power somehow, right? I need to reduce my power. I need to tell my inverter, act such that the power comes down. Because see, the load is here, right? The load is here. So the inverter should somehow act to see a smaller load or bigger resistor, as you mentioned, right? So to do that, inverter say, hey, just tell me how much you want. Tell me how much you want, I'll do. I'll take care of that, right? The IDQ control we talked about, right? The big control right now?
Let's say what the loader,
Huh?
let's say what the loader is within that, let's say 5 kilowatt.
No, you're going wrong way. You're going wrong way. You have it here. Go from here. How much power you have available? Load is over there. This is not load. This is grid, but I call it solid load. It's based on here how much you have here. You are matching here. Whatever you have here, you match it over there. So what we said we are here. 100, I don't know, 10, because this one is going up, you know, this is the opposite way, you know. So, yeah, well, okay, so let's say this is a 10 amp. This is the IPV here, not the IDC, this is the IPV. So we are here working at this point, right, is 100 volt. I want to increase my DC bus voltage. What should I do? I should bring down this current, right? Basically, look at here. When I'm going here, it's a little bit complicated, you know, because IDC is going to, I short circuit is going to go become more, right? But it's not going to jump. So this is we can see this is from here to here usually is 8 amps. This step maybe 0.1, 0.2 amps you go up. This one is almost constant from this step to this step, right? So you say this current is fixed, right? I want to increase my bus voltage. I'm going to reduce this one, right? This is like a pump, right? If this one is more than this one, I'm going to pump the voltage up. If this one is less than this one, I'm going to decrease this voltage, right? So basically, if I'm in this side of the curve, right, I have to reduce the voltage, right? What should I do? I should increase my IDC, right? So my point is, when you look at this system, to get to the VREF, we are receiving from the MPPT algorithm, right? VREF is coming from this algorithm, right? To get to that VREF, If we are less than that Vref, what we should do, we should reduce the P, right? Current means P, right? If the voltage is more than what we want, sorry, is less than what we want, what we should do, let me see, if the voltage is less than what we want, if this voltage is less than what we want, the power should reduce. If this voltage is more than what we want, the power should increase, right? Now, what we talked here, let me put it just here. If, I'm going to put it here, I sold more than IDC, so IC is going to be positive, so VC is going to increase, right? What is this one? What this one does mean here, P inverter, let's call it P inverter, should be what? I sold P inverter should be less than P sold, right? The voltage is the same for both of them, right? The voltage here, how much is the power by solar? Is current times voltage. How much is the power of inverter? This IDC times. At the steady state, they are the same. Both of them, they are the same, you know. But in the transient, is not, right? So, if the solar power is more than P in, you are going to increase the boss voltage. If I sold is less than IDC, right? Which means P sold is less than P inverter. So IC is going to be negative, right? So we are going to decrease it. So basically, what we can do here is P inverter is this P ref, right? Is this P ref. By changing this P ref, either reduce it or increase it. Let's say the inverter is working perfectly, right? As soon as I put my command here, my inverter is going to act and deliver that much power, right? So by changing this P ref, either increase it or decrease it, I can increase either my DC bus or decrease my DC bus, right? So basically, I can satisfy this one to either go this way or to go that way, right? Who is going to tell me which way to go? The MPPT algorithm, right? The MPPT algorithm is going to give me the Vref. It said Vref 100. Where I am right now, this is Vref. I am at 50 volts right now, right? What does it mean? MPPT is telling me what to do. It said I want 100 volts, but you are 50. What should I do? I should increase my voltage. Increasing my voltage means decreasing P in, right? P inverter, right? If I reduce my P inverter, so this one is going to go up. This one, either you can put it this way. This is a P sold. You can just put it here also. P sold, P inverter, and IC. You can do. If these two they are equal, means these two they are equal, right? This bus is not going to go anywhere. It's going to stay there. If this one is more than this bus is going to reduce. If this one is more than this bus is going to go up, right? So this is as simple as this. So by controlling the inverter power, I can control my DC bus to either go up or come down, right? Now, let's see how we can translate it to control. This is how it works, right? We talked about it, how we can increase the DC bus voltage, how we can decrease the DC bus voltage, but now see how we can put it in the control loop. So we have all these things here, right? I'm going to do this. And did I talk about Q or not? When I was discussing all these things, did I talk about Q? So Q is whatever you want. For example, unity power factor, keep Q ref 0, right? So I didn't talk about at all about Q, how much Q I want, right? So this thing was all related to active power. So basically, here, I'm going to do this. I have my Vref, right? Vref is coming from where? Do I have enough space to do this? I have my Vref. Vref is coming from where? Tell me now. This MPPT algorithm, we talked about it, which is going to get the I solar and V solar. It's going to measure those values and tell us how much is the VRAM, right? What else should we do? We said we should compare this one to what? VDC or VC. We call it usually VDC, right? We should compare it either VSOL, we call it, or VDC, doesn't matter. They are both the same, right? How much I want to be the error here? At the steady state. I want the VDC to be ref here, right? What do you think the output of this PI controller is? So PREF, I'm not going to put the number there anymore. It's going to come out of this control loop, right? This guy is going to see the difference, pass it to a controller, and say, hey, this much PREF. That much. It's going to do it automatically. It's going to calculate. This one we usually give it 0 for unit power factor. Right? Is it clear? What I did, I want to get to this voltage. How much is my voltage? Is this much. How much error I have? This much. I pass it through a PI controller. It's going to give me the command for PREF. And do that. Right? So you add this one to the what you had before. Just instead of PREF value, in phase 3, you set the PREF value, 50 kilowatt, 10 kilowatt, whatever is in the description how much you should put there. But on phase 3, PREF, because in phase 3 we have a battery here. When we have a battery, we cannot regulate the bus anymore. Whatever is the battery voltage is battery voltage, right? But when I have a solar, I can work at any point, right? Where do I want to work? Here. This is where I want to work, right? Why? Because it will give me the maximum power generation. Okay, this is exactly what is at home and everybody will see for this solar panel. This is what they have. I'm not sure that it's so good or not, because you know what's happening over there now. This is exactly what is happening in all the homes. In the homes, the only difference is a single phase inverter. I didn't talk about single phase inverter. We did talk about it, but not a controller. Very, very similar to this one. At one point, if you guys are interested, you can go, study that one yourself, or I can help you with that. But this is what you're going to do in the phase 4. Any question? I'm going to move on to the next. I said I'm going to put some document for a space vector up. I didn't put it, okay. The space vector. I'll put one picture for the incremental conductance method, and I upload this sheet, tonight hopefully I'll do all of it, hopefully. I'll upload all of them in the website, you have it up. But this is what, I'm gonna send you better, when I give you the phase 4, I'll give you a good picture of this one, I'll draw a block diagram for you guys here. And again, on your report, Arno put it there. Make sure you go through the steps, Usually, when you write a paper, I haven't written any paper for a long time. But usually, the sequence is like this. You come up with the abstract. Abstract, very quick. It will say what's the problem and what we did as an answer. What we did. Very quick, short. The next part, now is Arnold said put everything over there. Is the introduction. Introduction, you start to talk about this problem, what is the problem, what people they have done, blah, 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 those kind of things. The next part is you make experimental result. You put it there and say, this is the way I simulated, this is my control idea, looks like it's working in simulation, and the next phase is the experimental result. Sometimes the experimental result is not possible because it's very expensive, we cannot do those kind of things. But if you can do it, it would be great. Experimental result. And after that, you say, okay, I did this thing, you get to the conclusion. Now in the conclusion, you discuss it. What I did, and you explain, hey, before conclusion, here's another step, I forgot it. So you discuss your results. I did this simulation, this experimental, so we saw this kind of things and these things happen. And in conclusion, again, very short. You explain what happened. The problem was this, and we did this, and we got this good result or bad result, whatever it is, or this is the approach, Conclusion usually is short. And at the very end, you put your references. What was your references you used, in your report? So this format you should follow, for every report you're writing, every technical report. Now maybe something, I don't know, business report maybe is different, I don't know. But for technical report in engineering, this is the way you guys should go through it today. Any question here? I think we are done with this part. Just let me make sure to see I covered everything. We are going to go to the new topic now. When you do this simulation, so here, remember, you have another loop, right? And here, right? We have those things. They call this one internal loop, right? And this is the external loop. Usually, not usually, for sure, the external loop should be much slower than the internal loop. Why? Can somebody tell me? So if you look at it like this, I have a voltage loop here, and I have a current loop here, and I control blah blah, and I'm sensing current and I'm sensing voltage here. They call it internal loop, right? And external loop. This loop usually is at least 5 to 10 times slower than this one. What does it mean slower? Your changes here, you cannot change your values here faster than this one can respond, right? What you should do, look at here. So this signal, for example, should change like this. And here, if you look at this signal, it's going to go, for example, like this, like this, like this, right? This is how this system responds. If this value, this is this reference, right? And this system is going to respond like this. Now, look at here, I need this much time to get it stable, right? If I change my reference here, see the value was how much? It was here, right? It was not here. Now it's going to go start here. If I change it here, what is going to happen? This one didn't get here. Before getting here, you're changing, you get your. So your system, you're changing your reference much faster than what you can catch up, right? This is what's the problem, If you change your reference faster than what you can catch up, so never ever you're going to get to that reference, right? So basically, how this reference is coming is the result of this one, right? So this one should be 10 times by rule of thumb, slower than this. Slower than this. Now when you do the simulation, you get there, with the time constant and those kind of things you put in there, If you make the voltage loop much faster than the current loop, never ever you're going to get it done, It's not going to converge. Okay. Now, if today you are a good engineer to be able to design this thing, you get a call maybe 2 to 3 times every week for a job. People, they call you to find somebody who can design this kind of thing. Job well paid, 120K, 330K, something like that, just to let you know. Just before coming to the class, I don't want to move from San Diego. That's my problem, I wish I could move, I'm exaggerating, I would say, but every month I get like 5 to 6 good calls. I'm saying lots of them I ignore, even I don't look at them, But 5 to 6 of them, they are really good calls. I'm saying good company tempt you to talk to them. I know I'm not going to move, but still I want to talk to them because I'm sure I'm not going to move right now until even if GA kick me out, yeah, maybe I start to move. But right now I still have to say But this kind of thing, if you guys can do. The next part, this is inverter, very hot topic. So this is the one application. This is just solar. I went to something, I thought this is the best sense for you guys. You can get a kind of physical sense of what's happening because you see it everywhere. But this one could be an electric car. Basic is very similar to the electric car. All the changes around the command and those kind of things, how this control is going to happen, you know. If you look at the electric car, when you push the gas pedal, there's no gas pedal. I don't know how it is. I don't have an electric car, but I think to simulate it like a conventional car, you have a pedal, you can push it, and it's like gas pedal. What do you think you are doing?
Power.
Hmm?
Changing the power to
Changing
the
the
motor.
You're changing the P-run. That's the inverter. There's a three-phase motor, right? Instead of this one connected to the grid, this inverter is connected to a motor, right? If you want it faster, you need more power, right? You push this pedal, basically it's changing this reference value, make it bigger in the torque. It's torque, not power, but they're similar. Torque and power, you know, very similar. And you change that. And I'm saying, so this one, if you learn it, you know, this is something is very needed right now in the market. You know, everybody needs it for many, many applications. You know, this is one application I'm talking about. This is solar. It's going to be for UPS system. It's going to be for electric car. It's going to be for SVC. It's going to be for I don't know how many applications. And at the last session of class, I talked about some of the application of this kind of power electronics and those kind of things. But there is many, many applications for this one. You guys are not going to be expert by one class, to be honest. You know, very simple to do this way. But if you guys look at it, you like it, this is the start of this journey. You know, if you guys like it, you have to work more on it. See this controller you see here, this one here. I cannot program it myself. If you know how to program this one, they call it embedded engineer, software embedded engineer. See, all this calculation has to happen here. That's another job. They look for you like this, you know. You go like that, you know. They are looking for people they can do the program. This is C programming, but you need to be able to do program DSPs, you know. If today you guys are good, after this class I can find a job for you. To go start working for it. My point is, this is one application we talked. Now we're going to go to another one. That's a DC to DC converter, you know. And we'll start to talk about that one.
That's what I'm doing right now. Programming like a
I think most of you guys are junior or senior, am I right? Or grad, right? So you guys are going out of the school, you know. That's the reason I don't want to teach like power electronics 1 or energy conversion or power system that I'm going to teach later, you know. Those ones are going through the calculation, homeworks, problems, those kind of things. Because that one is building your base for this kind of thing. For example, energy conversion, the next course should be AC drive or machine control, you know, how to control, I don't know, permanent magnet machine, DC machine, I don't know, induction machine. That's another course I'm talking to the department, hopefully one day, maybe for 1 year from now, we'll add that one to the power course. It's going to be like this course. Now you guys know the inverter, but we go to the motor control. How you can control the motor, you know, those kind of things, you know, modeling, simulation, that one should be project based also, you know. That's what I like. I talk to the department, you know, they like to do it also, but right now we don't have resources for that to do it, you know. But this course is different from conventional course, and you can see you have 3 homeworks, I don't know, 1 final, 50% or more is project and simulation and those kind of things, you know. That was my intention, to keep you guys a little bit more connected to the real world, what is happening, instead of just doing simple homework, I don't know, those kind of things. You have done it enough, you know, up to this point. The next one we're going to talk about remember I talked about a state space. We said you have a system. I'll ask Arnold to do this homework, you know, quick homework for this one for you guys together with MATLAB, simulate, you know. If you have, this is your system. This system could be this inverter we talked about here, could be a radar system, could be, I don't know, whatever I'm talking, you know, it's not power electronics. If this system, it has an equation, they call it x dot is equal to ax plus bu. And CPX. I don't know what boy, I think we call it boy. I can formulate a system to have this kind of equation. They call it a state space equation. If I can formulate my system like this, means this system is done. Whatever I want, I apply my sources to this one. Inputs, U is the input vector. X is the state vector. U is the input. Input, I don't know, inputs, I'll call it just inputs. And Y is the output. You have a system, for example, in the system we had, if you look at it, what we did here, we had the inputs was the VDC, how much VDC we have, I don't know, grid voltage, those things, they are the inputs, right? Let's say we have a battery and grid voltage, right? The outputs are IDIQ, they are the state variable, right? IDIQ, they are the state variable. If I know IDIQ in that system, I can calculate anything I want in that system. You know, with those transformations, those kind of things I have, I can go calculate whatever I need, right? So at this time, I'm going to focus on how to calculate the state space equation. First for a buck converter, and after that a boost converter, just to get those equations first. Today, I don't know how far we are going to go, but that's the first thing we are going to do for the state space equation for a buck converter. Buck is the simplest circuit, right? In the power electronics we have, that's a buck. Our boost, those two, they are very simple. We'll go through those ones to see how we can calculate this state equation. We call it average state space equation. Call it average state space equation. This is the, if you want to start to read it, Appendix B of the Daniel Hart book. It's a pretty good, you know, he explained it pretty well. I'm going to go through that book, you know, here. Appendix B of this book, you know, he's explaining it for, I think he's explaining it for Bob, but I'll do it for Boost also. After we do this one, we calculate the state space average model of the buck converter and boost converter. Maybe Thursday or next week, we're going to get to the control part. To go to the control part, we need to get a small signal model. A small signal model of the system. That one is going to be a little bit more back. Let me put the converter here, how the system works. We have a, I call it converter or power plant. For example, this converter, for example, is the buck converter or the boost converter or whatever, right? So what we want to do, for example, we want VDC ramp, right? I want to control the output voltage of this converter. Let's say, just I'm going to put it this way, right? This is the V out. Right? So this one is going to come to block. It could be as simple as a PI, but usually for DC to DC converter, they call it compensated error amplifier. The name they put for this one is a compensated error amplifier. But could be a PI. You know what I'm saying? It still is a controller. You know, compensated error amplifier. Every DC to DC converter has this one. We call it compensated. We'll talk about it in detail, you know, later. We need to design this. The intention of this one is like a PI controller. We do it for analog circuit. You want to build it with op-amp, resistor, those kind of things. This is the second simulation. Arno is going to give you, the first simulation will give you the, you saw it already, I'm not sure or not, is a flyback converter. Did you look at that? Did you see that one? The flyback converter. There is a PI controller. If you look at it, there's a PI. PI is a DSP. See, this is the advantage of digital signal processing. You know, That PI, I gave you the equation, and you can go implement it in the DSP, right? And you build that one. You don't need to build any circuit. But if you go back 20 years ago, when the digital processor, they were not this much strong, and we didn't have a good microcontroller, they used to do everything analog. Everything was analog, you know. Analog has these good things, you know, the bandwidth is very, very wide bandwidth, it's very, very wide bandwidth compared to the digital. Because analog, you sample the signal at what rate? When you're working with analog signal. At infinity, right? I mean, you have the sample at any moment, right? It's continuous. But when you go with a digital signal processor, you sample here, you do your calculation, again you do sample here. They call it sampling, you know, frequency, right? You do your calculation. So the bigger the sampling frequency, the less bandwidth, right? Why? Because you don't know what's happening in the middle, right? You're missing that part. You're assuming, hey, it's going to come through here. You know, at this point, I'm going to sample another one, do my calculation, and change my I don't know, control values, right? But the analog system is continuous. Is doing it every moment, right? The bandwidth is much wider. But they are expensive. They are difficult to design. Digital controller, they are much more, you know, flexible. And most of people now they use the digital controller. Now, we call this one compensated error amplifier. On the flyback converter you guys are working with, it's called just PI. It's called just PI, and you see the rest. The output of this one is going to give you the, I'm going to call it VC or VD. Let's for now, let's say VC. VC is a V control. V control, right? Control signal is going to come out of this one. And after this one, you are going to have a PWM generator. Remember when I was teaching power electronics 1, when I was doing all this waveform, up here I put a gate here, on, off, right? And I say, hey, I don't care what is that. Just I put on, how we create that one. Just I put the on, off, right? That on, off is the output of this PWM generator. It's going to send this signal to the converter. On, off signal, right? To the switch. Turn on, turn off, turn on, turn off. So here you could have a feedback signal, like a signal conditioning or whatever, or it could be a unity feedback, right? Based on what you have. This one comes here, and this one comes here. This is a control loop for a DC to DC converter. It could be buck converter, boost converter, whatever. It could be any kind of converter. It could be flyback, could be buck boost, could be forward converter. This is in general what it is, right? Now, we will talk about this one, what it is. There is a kind of a standard, blocks for this one. This one is a standard block. We know what are this one. In this one, there is some unknown. I have to define them, how much they are. But the block is a standard, like a PI, right? It's a KP plus KI over S, right? But I need to design KP and KI, right? Here is the same thing. If you are going to do analog circuit, it's a kind of combination of R, C, and op-amp, those kind of things. But how much R? How much C? Those things you need to design, That's a part of design. So my point is, this one, the structure is known, but you have to define the values for that structure, those parameters we have in this structure. The same thing here. Converter is the buck, boost, whatever it is, right? This is a control problem right now, right? If I can get the math model for this one, I'm done. I don't care what is the converter anymore. If I'm a mathematician, if you look at most of control guys, they know mathematics very well. They don't know that much about what's the power system and those kind of things. And they do a lot of math here inside this loop. So we need to give them a model, math model for this system. It's this. I need to give them this model. If they have this model, they don't care if it is a buck converter or is, I don't know, what should I say? Is a pot you are cooking, rice. You know what I'm saying? Just give them this model. They are going to look at this model. That's all they want to know. You know what I'm saying? This is important for them. And from this point after, they don't care what is that. They want the transfer function of this system, right? Now we're going to work on this part to get this one known. We'll get this one for this part. We do it for buck and boost converter. After we got these things, we'll come back to this model. This is the feedback. Feedback gain. Back gain. After we have this one, right, and we'll say what's the structure for these two, so we can put the models together. Now we'll tell you guys, hey, go design this value for this error amplifier. Go select those RC values. Or if it's a PI, go select the PI values for this one. You can go back when we finish this one. If you are interested, go look at the one fallback is a little bit more complicated to get this model. But if you are interested, do it. The next homework is going to give you is the buck converter with the analog, this one. You know what I'm saying? Analog. Just go design that one for yourself with what I'm telling you. Right now you cannot because you don't know really how to design it. But when we go through this one, you guys go back, look at that homework, and say, oh no, I can calculate it. Or no, give me these values, RC values for this one. But I can go calculate it myself. You know, it doesn't have to give it to me. I can go design it. And this is the difference between a good designer and bad designer. A good designer designs a system with a very critical damping, because quickly you're going to get to what you want to go without any overshoot, right? But a bad designer is going to get a big overshoot, right? What's the example for a big overshoot? What's the bad thing? What's a big overshoot?
Car.
Let's go think about car, right? If the system is not critical damped or over damped, when you hit the brake, you know, you're supposed to stop there, right? If when you push the brake, there's an overshoot. What does it mean? The reference is there. For example, it's very bright sitting, you know, next to that, you know, camera, right? So you push the brake, but there's an overshoot. What is going to happen? You're going to go 5 meters more, and you're going to come back, right? But there is a wall. 2 meters later, there's a wall, right? You're going to hit the wall. So you're not going to go 5 meters and come back. You know, boom. You're going to hit the wall, right? This is a bad design. You know what I'm saying? It's the exact control system. Just I'm trying to give you this example. You can feel it better. You know what I'm saying? What's bad things about overshoot? You know, you're going to pass your reference. Sometimes it's okay. Sometimes it's not. Right? You pass the reference, something bad is going to happen. You know, for example, if you have a current for this module, this IDIQ. I don't know, let me see this one. How much is the current rate? This is a 100 amps module, right? Usually when there's 100 amps, the rule of thumb is just use it for 50 amps maximum. You know what I'm saying? 50 amps, for example, if I want to design this circuit, I said, okay, the maximum value I can pass through this module is 50 amps maximum. How much is the RMS divided by square root 2? How much is it? I don't know. Let's say square root of 2 is 2 is 25 amps, you know, RMS, right? So I can have 25 amps RMS. So the reason we are doing it, we know when we design the control. You know, if you're going to go to 25 amps, I'm not going to go perfectly to 25. I'm going to have some overshoot, right? So maybe I'll go to 30 and come back to 25, right? That's fine. 30 means 70, right? 60, it means 60 because still this module is good. It's not going to burn. But if I have a bad design, right? So let's say I said I'm going to use it for 40 amps. Now I have a 150% overshoot. So this one is going to go to more than 100 amps. Boom. This one is going to blow off, right? So these are the design. I'm saying when you design this thing, you should consider all these things in the equation. You know what is going to happen if I have this much overshoot. Usually you design it for 20% overshoot. You know, keep that one in mind. You know, if you can keep it under 20% is pretty good. It's pretty good. You know, but if you have a really bad design, you should select a 200 amps module. You know, make sure you're not going to blow it up. You know what I'm saying? So for 200 amps, you have to pay more money, right? Now we will get the model for this one, and after that we talk about this one. This is very simple. This is a very simple model. This is usually we use the gain we choose it here 1. But if you look at this one, for example, this guy, they have a simple transfer function. For example, we have for this one, it's sensing if they have 480 volt system, right? How much is this peak? 480 times the square root of 2, right? We are bringing a phase voltage here. Just I want to show you how much gain is going to be in this circuit. So, how much is the maximum phase? Phase is going to be 480 square root 2 divided by square root of 3, and this is how much? This is a minus 480 square root 2 over square root 3. I don't know how much is this. So let's say this is 300, right? And this is minus 300, right? So peak to peak is how much? Minus is 600, right? How much voltage I can bring to my DSP? 0 to 3.3. The signal I'm bringing to my DSP is going to be 0 to 3.3. How much I have here? Minus 300 to 300. So first of all, what should I do? Let's just do this way. So let's say this 3 volt. Usually we don't go to 3.8, keep a little bit margin, you know. If something goes wrong, you know, still you don't burn your ATDs, because as soon as you burn the ATDs of the DSP, looks like you put a nail in his eyes, you know. He's not going to see anything. He cannot see anything anymore, right? The controller is going to go crazy, you know. We cannot do anything. So if it's 0 to 3, basically this signal should translate to this, right? Right? So first of all, 600 should go to how much? 300. So sorry, 3. So 600 divided by 3 is 200, right? So I should have a gain of 1 over 200. That's the first thing. I should bring this signal times by this one, right? If I do this one, it's going to be 1.5 minus 1.5, right? Still is not good.
You offset.
Offset. Get it offset. You put a 1.5 here, and you do it this way. So this is your feedback loop, right? 1.5 is the offset. As soon as you get it to the DSP, so you get this signal. Here you say minus 1.5 because I want this one, right? And after that, you time it by 200. You get the you build the real signal you have. You know what I'm saying? This is what you do. To bring it in DSP into the DSP, you have to do these things, right? Because if it's more than 3 volts, it's not going to come to the DSP, right? You have to make everything small, but when you get to the DSP, I need to do all this calculation. I cannot do with I shouldn't do with 3 volts, you know, because my real voltage is 480 volts, right? I'm going to take it back to what it was, right? So this is a kind of feedback, gain feedback here for this system when you do this. But in general, it's a little bit simple. Either one, we don't care. We don't go with the limitation of the DSP and A to Ds, you know. We just keep it maybe 1 or whatever, K. We put a gain of K over there and make it simple, okay? Now, let's talk about the buck converter. I want to finish buck converter. I'm going to talk about 10 minutes about what we talked, and have 1 hour to go talk about this, and now we have 15 minutes. So, if you look at the buck converter, I'm really bad to remember how the circuit is. This is the buck converter. I do the simplest case. I'll tell you why I'm saying call it simplest case. Because this inductor has what? Every inductor has a resistor, right? If you're going to make it, I'm going to give you this one in homework. You guys give me the homework. RL. Right? This guy. I'm not going to do any of this one, you know, just because the calculation is going to get crazy, you know, but you can do that at home. You can spend time on it. And how about that?
Yes.
How about switch? Right? There are more. You know, if you want, here there is a stray inductance, you know, but you don't go that much further down, you know, because it's going to calculation. But let's erase all those things. We go with the ideal case. No on, no on. is the VO, which is equal to VC. This is the IL, VM. Before I start to calculate to model this thing, this switch has a duty cycle, right? Is on for D and is off if you look at the gate signal, right? It's gonna be like this. How much is this one? And how much is this one? So keep this one in mind. You know, we went through everything for this circuit. When the switch is on, we have one circuit, right? When the switch is off, we have another circuit, right? So when the switch is on, let's say switch is on. Let's say I calculated my equation. I call it X is equal to, oh, I forgot X. X in this circuit, how much is it? Put a VCIL or ILVC, just I will go with the same way I'm doing it. ILVC. You know, IL and current of the inductors and voltage of capacitors, they are the state variable. You know, you should know this one from circuit theory, you know. Inductor current and the capacitor voltage, they are the state variable. If I know IL and VC, this circuit is known. I know it. Now, doesn't matter if this switch is on or off, I have IL and VC. So X is not going to change, right? I have two equations. If the switch is on, X dot is equal to AX plus A1. A is a kind of dependent to the circuits. What values I have in my circuit, what values I don't have, plus B1 U. When the switch, and I have a Y, I'm just going to call it Y, or let me use the same notation. You use a VO. In this case, this is a VO, but let's use this one. VO is a C transpose. So VO, see, in this circuit, you want to know the VO, right? You want to calculate the VO, which is a VC. In this case, it's a VC. But just I'm putting it kind of to formulate this system. It's going to be CT1 times X, right? When the switch is on, I have some elements, keep in mind. If I'm going to have something like that. When the switch is off, right, X dot is X dot. So it's going to be A2, but the circuit is going to change. A2X plus B2U, and VO is going to be C2T times X. Right? So if the switch is on, is this. If the switch is off, is this. So tell me something I can use for any time. I don't know if the switch is on or off. This switch is switching by 50 kilohertz, right? I don't know, switch is on or off at this time. Give me an equation I can use it for any time. How? Can you tell me? Can you tell me if somebody can guess? Huh? So there is a switching, right? There is a switching frequency, for example, 20 kilohertz, 50 kilohertz, right? For example, if 50 kilohertz, I don't know, 1 over 50 kilohertz, how much is it there? For example, 10 millisecond. 10 millisecond, we have this circuit, right? So out of this 10 millisecond, let's say the duty cycle is 30%, for example. So 3 milliseconds, the circuit is on. 7 milliseconds, the circuit is off. 3 milliseconds, I have this one. 7 milliseconds, I have this one. What should I do? Average, exactly. If I want to do, I'm going to average it out, right? How much is I have the equation top up there? V. How much I have this equation down there? 1 minus V, right? So I'll put it this way. I said, this is a state, X dot is going to be A1D. A1 is a matrix, D is a percent, you know, 30%, 40% is a scalar, right? just pick it, plus A2 times what? 1 minus D exactly. Times what? X. Plus, go and come here. How much I have B1? Plus how about C? Which is here VO basically, here in this case is the VO side. How about VO? D this one, 1 minus D this one, right? So it's going to be D CT C1, sorry, C1T and C2T right? So this equation is going to, I can average it out. You know, it's not going to be very accurate, right? Why? Let's say it's not accurate. If you look at the inductor current, think about it. I'm going to put for the steady state. Inductor current, remember, it was like this, right? Right? We have a ripple on it, right? When it's on, it's going to go off. When it's off, it's going to come down, right? I'm telling you, hey, I cannot tell you exactly how much it is, but by this equation, I tell you this much. I give you average of this value, right? This method is going to give me this one. It's going to give me this one because I averaged it out, right? I averaged it out. But this is the real current. It's not going to give me the real current. They call it average method. This is the average method, you know. It's not going to go to the detail of switching, but for the control purposes, it's okay. Because this is, at the end of the day, this is the one where, yeah, you have some little here. You're going to get there. But if the average gets there, this is what we want, right? I can control the ripple with the inductor value, with the switching frequency, right? I can reduce it. So if I can get my average where I want, so I have done my task, right? I've completed my task, right? So basically this method is going to give you this one, not this. I'm not going to push you a lot because if I want to do that one, I'll tell you to simulate a buck converter with the just regular switching, you know, just go calculate this current. Now, build a circuit, X dot equal down, right? With this method, and go plot the output. So that one is going to give you this one, the real circuit is going to give you this one, you know what I'm saying? And you can see, hey, this is happening in the reality, this is happening in math world, right? But it's good enough. Why? Because I'm going to use this one for my control design, right? This is what I want to use for my control design. Because it's easier, it's much easier. That's math equation, those things are not there. Now, we have this one. I'm going to stop here, I'm not going to go further because the goal is for the buck and boost converter to get this equation. And after that, we go to the small signal. I think next class we'll finish the steady state for buck boost, and hopefully we'll get to the small signal. I'll stop. Question? So if you have any question, don't leave it for the, I think today was the last day you can ask your question. You know? If you have a question, go ask him tonight, after tonight, you know. Don't leave it for later.